look at this circuit and consider the potential at this point as 0. So this is according to mathematics, but that's not how reality works, isn't it? Tau is C equivalent into R, so we need to calculate C equivalent. So hello everyone and welcome to LN Overseas. So I'm back with a series that is 45 topics in 45 days. In this series we take 45 topics, 15 from each subject, and today we're going to take a topic from physics, and that is the RC circuits. RC circuits, also known as the transient state of capacitors. So when I talk about capacitors, there is a state where the charge on the capacitor is 0. There is another state when the capacitor is completely charged. But this doesn't happen in an instant, isn't it? So it will take some time. Although I completely agree that time will be quite less. However, when we talk about some complex circuit, that time matters. Getting the point? So here we are going to learn that what is going to happen from the 0 state to the steady state. Are you ready? RC circuit. First of all, when I talk about RC circuit, it will consist of a resistor, a capacitor, RC. Yeah, duh. And in order to make a simple RC circuit, you need 3 ingredients. What are those 3 ingredients? One capacitor, one resistor, and a battery. How to make a standard RC circuit? What is the recipe? Connect them in series. Yeah. And in order for that RC circuit to qualify as standard, there is one more important thing, and that is that initially capacitor must be uncharged. So the initial charge of the capacitor must be 0. Okay, agreed, sir. Then what about the other state, sir? What about the other circuit where capacitor is there? It could be any RC circuit, non-standard RC circuit, right? There you could have another resistor instead of a battery, right? Or maybe a combination of that. There will be some circuits where I can convert that complex circuit into a standard one. Getting the point? Yeah. Yeah. We are getting the gist, sir. Okay, nice. So now, let us consider the standard RC circuit and let us try to understand what is going to happen in this transient state. Or in other words, let us see what is going to happen when the capacitor is charging. Alright? Okay. So charging of a capacitor. So initially you have a standard RC circuit. Initial charge is 0, resistance is there, a battery is there with EMF E, ideal battery. Okay. Now if you look at this circuit and consider the potential at this point as 0. Yeah, I can consider potential at any point as 0 because Ohm's law allow me, right? That is the potential difference that we require. So what will be the potential of this point? That will be the basic. If this is E, this is E. Yeah. If charge on the capacitor is 0, what will be the potential drop across the capacitor? That is 0. Potential difference is 0, right? So potential of this point is E. Any problem? Yeah. If this is 0, this is 0. Yeah. If that is the case, what will be the current across the resistor? That is E is equals to IR. So I is equals to E by R. Yeah. Basic. No rocket science. So if that is the case, what is the use of this capacitor? Nothing. Nothing, right? Yeah. So initially there is a capacitor, and when I just connected this circuit, what is going to happen? Current I is suppose going to flow. That current across the resistor will be same, and that is E by R. Yeah. So removing the capacitor and replacing it with a general wire, right, could be a choice in order to understand this situation only. So just after completing the circuit, capacitor will behave as a short circuit, or it is nothing but a wire. Basic. Why? Because no potential drop is there, na? Basic. Okay. But what is going to happen after some time? The potential difference begins to generate, right? So at time t, the charge on the capacitor will be equals to Q by C. Agreed? This thing will be equals to Q by C. Yeah. At any time, right? Q is any instantaneous charge. Okay. Q is the charge at this time t, right? A potential drop across this capacitor will be Q by C. Q is equal to CV. Okay. Q is equals to CV. Till when it is going to get charged? When it is going to be completely charged, the potential of this terminal of battery will become equal to the potential of this plate. Potential of this terminal of the battery is going to be equals to potential of this plate, and when this is going to happen, the current will stop. Yes or no? Isn't it? There is no what do we say, connection between the two plates. No connection between the two plates. So if potential difference across the battery is equal to potential difference across the capacitor, the current is going to stop. Simple. That is the general realization that I have. Let us realize this thing mathematically. Okay. Alright. So at any time t, let us analyze the circuit. Okay. If that is the case, plus minus, can I apply Kirchhoff's law? Yeah, I can. Let us try and do that. So starting from here, I can write, I am going from high potential to low potential like this, right? This is my traverse, high potential to low potential. So I am going from high to low, that means it will be negative Q by C. Again high potential to low potential minus IR, if I is the current in the circuit. Then I am coming here, I am going from low to high. So plus E is equals to 0. Right? Make I as the subject. IR will be equals to E minus Q by C, right? Or EC minus Q by C, or I will be equals to CE minus Q divided by R. Now current in the circuit is how much? Sir, dq by dt. dq by dt. So this thing is equal to CE minus Q by RC. Such a nice differential equation, a variable separable differential equation. So solve it. So dq over CE minus Q is equals to 1 by RC dt. Now I am talking about how much is the charge at any time t. I am saying at t is equals to t, charge is equals to say Q, and at t is equals to 0, the capacitor was uncharged, absolutely Q was 0. So I have my limits, right? I know my limits, definitely I know. So this thing is equal to 0 to t, so this is going to vary from 0 to Q. Yeah. Integrate this thing. So this will be ln CE minus Q over minus 1. Yeah. Is equals to T by RC. Right. I have substituted the limits. Most basic integral ever. Take negative onto the other side. That will be easier for us later on. So this will be ln CE minus Q, right? CE minus Q over, if you substitute Q as 0, it will be CE only, right? So ln CE minus Q minus ln CE, so it will be ln CE minus Q by ln CE is equals to minus T by RC. No rocket science. So CE minus Q over CE is equals to e to the power of minus T by RC. Yeah, the Euler's number. And at last, I can get Q as CE 1 minus e to the power minus T by RC. So this is Q as a function of time. So this equation will tell you that how much will be the charge at any time t on the capacitor plate, right? Plus Q minus Q, right? Now they can ask you that, tell us that what will be the time at which the capacitor will be charged to half of its charge value, right? So what will be the maximum charge? Maximum charge is equals to Q is equals to CV, right? Or that is equal to C, isn't it? When the capacitor is completely charged, we know Q naught is equal to C. So in that case, if I have to get the half of the maximum value, so value of Q they have given us as C by 2, half of the maximum value. This thing is equals to CE 1 minus e to the power minus T by RC, and you can calculate time from here, can't you? Yeah. So they can give you that, okay, in how much time it will be charged to 1/4 of its value, of its maximum value. Yeah, we can use that thing. So we have a nice equation of charge. Charge is equal to C 1 minus e to the power minus T by RC, right? Can I calculate current in the circuit using this? Yeah, basically current is dq over dt. Differentiate that thing up. So this thing will be equals to C will be constant, that will be 0. This is E, so this will be CE, negative will become positive, by RC times e to the power minus T by RC. This is E by R, e to the power minus T by RC. This is your current. Basic, no rocket science. Yeah. So how will be the graphs? Let us see. So QT graph, yeah, QT graph will be something like this, right? A kind of rise where it will become saturated. After some time, the capacitor will definitely get completely charged, right? Although according to the mathematics, that will be at t, that will be when t tends to infinity. So this is according to mathematics, but that's not how reality works, isn't it? So what is the maximum value? That is C, we just discussed. What about IT curve? So initially the current is maximum. And when the capacitor gets charged, the current is dropping down. Current is decreasing. And at last, the capacitor will work as an open circuit. So current will drop to 0. The current will stop flowing in the circuit when the potential of this point will become potential of this point, potential of this point will become potential of this point. That's how things work. So the curve will be a decay curve. And this will be E by R e to the power minus T by RC. What will be the maximum value? Maximum value of current is at the beginning, when the capacitor was behaving as a short circuit, E by R, isn't it? What if I have to calculate the potential drop across the resistor? That is equal to IR. At any instant, substitute the value of I, right? So potential difference across the resistor will follow the same curve, agreed? What will be the potential difference across the capacitor? That is Q by C. So it will follow this curve, isn't it? Substitute the value of Q, right? Substitute the value of Q, you will get Vc. Substitute the value of I here, you will get the value of Vr. When you are going to add them together, you will get E, right? Try. Alright, interesting. Moving ahead, let us talk about time constant. The product of RC is called time constant. Now this is a currency. This is a currency which will tell you that how much the circuit has been charged, or how the circuit is at which instant. And also in reality this works as a parameter to determine how readily a circuit is going to get charged. If time constant is less, the circuit will get charged quicker. If time constant is more, the circuit will take its time to get charged, right? Okay. So the product of RC is called time constant, right? Tau, right? This is tau. Okay, nice. So how this currency is useful to us? Okay, let us see. We have Q is equal to CE 1 minus e to the power minus t by RC. Let us see what is going to happen in one time constant. That means at t is equal to RC. At t is equal to RC, what is going to happen? Substitute 1 minus e to the power minus RC by RC. This gets cancelled, right? This will be 1 by E. E has a value of 2.71, right? And when you substitute the value, you will get it as 0.63 CE. 62.8 something, 63E, right? So this is the value of charge in one time constant. What is C? CE is the maximum charge, isn't it? So that means 63% of job is done. 63% of the job is done in one time constant, right? You can define time constant using this as well. What about current? When you substitute the value of T as tau, T as RC, in the current equation you will get it as 0.37 into P by R. So this is the maximum current. So the maximum current in the circuit in one time constant is 0.37. So that means 37% job is done. Absolutely no. Why? Because current is decreasing. Current is decreasing and still 63% job is done because it is decreasing. So 37% is left. Here as charge is increasing, so job done is 63%, right? So the charge will be 63% of the maximum charge, and here 37% of the maximum current. And for simplicity's sake, right, as I said, mathematically the capacitor will be charged at t is when t tends to infinity. But in reality, in two time constants, the charge on the capacitor will be 84% approximately. In 3 time constant, it will be 95%, and in 5 time constants, right, the circuit will be approximately 99.9% charged. So in 5 time constant, the circuit is almost at the steady state. So we say the circuit will be completely charged in 5 time constant, not when time tends to infinity. It will not take forever for that capacitor to get charged. Getting the point? Yeah. So in one time constant, 63% of the job is done. Charge is increasing, so 63% of the maximum charge, current is decreasing. So 63% has been decreased. So this much remains. Okay. Let us take a question. A parallel plate capacitor C with plates of unit area and separation D is filled with a liquid of dielectric constant K is equals to 2. The level of liquid is d by 3 initially. Suppose liquid level decreases at a constant speed v, the time constant as a function of time t is. So we need to calculate time constant as a function of time. Okay, nice. Look at this capacitor. So something is filled here, liquid with dielectric constant K, and that is flowing out. Somehow it is flowing out. Sir, how? Don't know, don't care. So it is flowing out. So when you look at this configuration at any time t, you are going to find there are two capacitors that are connected in series. Absolutely. So this is one capacitor, this is another capacitor, right? If I calculate the net capacitance, can I convert this thing into standard RC circuit? One capacitor will be there, one resistor will be there, E will be there. So time constant for this configuration will be equal to C equivalent into R. Is MOS clear? Yeah. So tau is C equivalent into R, so we need to calculate C equivalent. So let us zoom into this, right? At any time t, if V is the velocity with which it is flowing out, what will be the width? What will be the width that is remaining? D by 3 was initial. At any time t, it will be d by 3 minus Vt, right? D by 3 minus Vt. Yeah. So they are saying that the depth is decreasing with the velocity V. So it will be d by 3 minus Vt. And suppose remaining is d dash, right? What will be this d dash? D dash will be d, the total distance d, minus d by 3 minus Vt. Agree? So this thing will be equals to 2d by 3 plus Vt. 2d by 3 plus Vt, yeah. This is 2d by 3 initially, and it will increase with the same rate. Okay. What will be C equivalent? Let us calculate. 1 by C equivalent will be equal to 1 by C1 plus 1 by C2. Isn't it? This is one capacitor C1. This is second capacitor C2. They are in series. Okay. What will be C1? C1 will be epsilon naught A by D, right? By D, what is D? That is 2d by 3 plus Vt. Agreed? Absorb. Yeah. Sir, epsilon on A by D, so D is at any instant is this thing. So that suffices. What will be C2? It will be epsilon naught A. Epsilon A. Why epsilon A? This is vacuum, this is not vacuum, right? This is some material. And what will be the width? D by 3 minus Vt. So this thing will be equals to 2d by 3 plus Vt plus d by 3 minus Vt over epsilon naught A. And here can I write epsilon as epsilon naught into K? Yeah, I can. I definitely can. And if I take the LCM, can I multiply and divide it by K? Yeah, that I can. So this thing will become 2kd by 3 plus kVt plus d by 3 minus Vt over epsilon naught A into K. This is 1 by C equivalent, right? 1 by C equivalent. Value of K is given to us. Can we substitute? Definitely you can. So 1 by C equivalent will be equals to 2 times 2, that is 4d by 3 plus 2 Vt plus d by 3 minus Vt divided by 2 epsilon naught A, right? Can I take the reciprocal? Epsilon naught A is equals to 2 epsilon naught A by 5 d by 3 plus Vt. Take the LCM, throw 3 in the numerator, so this thing will be equal to 6 epsilon naught A over 5d plus 3 Vt. This is your C equivalent. If you have C equivalent, what will be the time constant? Time constant is C equivalent into R, that is 6 epsilon naught A into R over 5d plus 3v. No rocket science, right? Seems overwhelming, quite basic, right? Moving ahead, let us talk about the discharging of the RC circuit. Now in this case, you have a capacitor that is already charged. Initial charge is Q. Completely charged, initial charge is Q, right? And I have completed the circuit. What is going to happen? The capacitor will get discharged. Energy of the capacitor will be dissipated across the resistor. General sense. So now in this case, what will be the current? Suppose this is positive, this is negative, this is current. So current is dq by dt. Are you sure? Is the capacitor charging now or discharging? It is discharging. So charge on the capacitor is decreasing, right? So this thing will be minus dq by dt, right? Yeah. Now everything is easy. Apply KVL. Minus q by c plus IR is equal to 0, right? So q by c R is equals to I. So q by RC is equals to minus dq by dt, right? Or minus dt by RC is equals to dq by q. And now when you are going to integrate this thing, this will be from 0 to t, and now this will be from q to any charge q. At time t, it is q. At t is equal to 0, charge is q, right? And at t is equal to t, charge is any charge q. So integrate this thing. What you will have? You will have minus t by RC is equals to q by, ln q by q naught, right? Ln q by q. Yeah. So from here, q is equals to q e to the power minus t by RC. The charge is going to decrease. Yeah. What about current? Minus dq by dt. So minus, differentiate this thing. This will be equals to minus of q by RC, and this will be plus e to the power minus t by RC. This will be a current, right? And whatever will be the energy across the capacitor, whatever will be the energy stored in the capacitor, that will be dissipated across the resistor. So current will also decrease. Charge on the capacitor will also decrease. Getting the point? Yeah. So graphs, let us see. So QT graph, decay. What is the maximum value? Q. IT graph, decay. What will be the maximum value? Q by RC, right? This is Q is equals to Q naught e to the power minus t by RC. This is Q by RC e to the power minus t by RC, right? So in this case, they can ask you that calculate a time in which 50% of the charge remains, right? So that means 50% of the charge remains, that means Q by 2 is remaining. This is Q times e to the power minus t by RC. Calculate time from here. Simple. Same for current. Okay, nice, interesting. Yeah, let us summarize. Let us summarize. For charging case, you have at any time t, q is c 1 minus e to the power minus t by rc, I is e by r e to the power minus t by rc. When time is 0, charge is 0. When time is 0, current is e by r, right? In one time constant, charge is 63% of the job is done. So charge is 63% of the maximum charge, final charge. And here 63% of the job is done. So current has been reduced by 63%. So 37 remains. 37% remains. At infinity, charge will be C, current drops to 0. In discharging case, again there will be time constant that is defined. So T will be Q times e to the power minus T by Rc. I is Q by Rc times e to the power minus T by Rc. Initially, charge is Q and current is Q by Rc. Q by Rc basic. Tau, in one time constant, 63% of the job is done. So now charge is decreasing in this case. So 37% remains. Here as well, current is decreasing, 63% of the job is done, so 37% remains. At infinity, charge will drop to 0. The current will also drop to 0. Getting it? So that's all for the day. I hope you have enjoyed this session and you can continue watching the playlist. The link of the playlist is given in the description. If you have any queries, any doubts, any problems, you can drop them in the comment box. So thank you. Have a nice day ahead.